Let's talk about estimating sums. So if we know that a series is converging, what that means is that it is converging to a finite value s. We call that the sum. We'll just let s represent the sum of a converging series. And if we have used a partial sum, so s sub n, the partial sum, the sum of the first n terms. Well, if we use a partial sum as an estimate, then what we call the error or the remainder is the difference between the actual sum and the partial sum that we've used. So let's just take an example. Let's suppose we have a series that's converging and we say, you know what, I want an estimate. I know it's converging. I don't know exactly what it converges to. I'm going to go ahead and add up the first 100 terms. So take the 100th partial sum. Then that 100th partial sum will be an approximation of the actual sum, and the remainder, the error, would be the difference between the actual sum and the partial sum that I use. So if we took the difference between those two, that would be what we call the remainder of, or the error in using the first 100 terms. So how far are we off from the actual sum? Well, it would just be the difference. Now, if the terms are all positive, we wouldn't need this absolute value, but we'll put this absolute value around in this general definition of what we call the remainder. Okay, so let's take a look at using remainders and the integral test together. So here on the screen, what you can see is the integral of function. You can see the integral and you can see the idea of the remainder. So remember, when we're talking about a remainder, it's the difference between the actual sum and the sum of the first n terms. So if we've added up the first n terms, then we have n plus 1 to infinity terms left to add up. So that's what the remainder would be representing. And so what you can see right here is you can see the a sub n plus 1 term, a sub n plus 2, a sub n plus 3 term in a Riemann sum. So if we build these Riemann sums using the left-hand endpoints to create this Riemann sum of an infinite number of terms from n plus 1 on, which would be the remainder. And then you can see the integral from n plus 1 to infinity. That would be this area right here. So you can see, based on these two graphs, this is a graphical proof of where this remainder theorem I'm going to give you comes from for the integral test. But you can see that this remainder is going to be bigger than the integral from n plus 1 to infinity of f of x. And in a similar way, if we use the right-hand endpoints to draw in our Riemann sum, you can see those rectangles, a sub n plus 1, a sub n plus 2, a sub n plus 3, going on and on and on. Well, this would be the remainder as well. This would also represent the remainder. But you can see if we integrated, this would be the area that we would be estimating by that Riemann sum, would be the area not from n plus 1, but from n to infinity. And you can see from n to infinity that remainder, that r sub n that we're discussing, is actually going to be less than or equal to the integral from n to infinity. And what that does is that gives us a remainder estimate for the integral test. So again, the integral test is only telling us if a series is converging or diverging. It doesn't tell us what the series is actually converging to. So if we want to know what the series is converging to or get an estimate for what the series is converging to, we can use the following remainder estimate. And the remainder estimate says this. It says, again, because we have to guarantee that we have a continuous positive and eventually decreasing function on the interval from n to infinity, and that function on the integers is equal to each of the terms in my series, then the sum of the series, if we have a convergent series, the sum we're going to let equal s, and s sub n be the partial sum of the first n terms. Then the remainder is the difference between the actual sum and the partial sum. We can think of it as the error that is left when we use the first n terms, the s sub n term, to estimate the actual sum. And that remainder is going to be between the two integrals that were described on the graph that I first showed on the screen. So the remainder is going to be between the integral from, it's going to be less than or equal to the integral from n to infinity of f of x and greater than or equal to the integral from n plus 1 to infinity of f of x. Now, I will say this, we tend to focus more on the right side of this bound. We tend to want to know that the remainder is less than or equal to some number. So we tend to prefer just to look at the right side of this integral, but sometimes, or of this inequality with these two integrals, but sometimes we look at the left side as well. Then if we just think about how R sub n is defined, knowing that R sub n is actually equal to S minus S sub n, if we were to plug that in, and S, by the way, is the actual sum of the series. So if we were to plug that in, we could get the following result that we have on the last line here of this remainder estimate, that the actual series itself, that's my S value, that the series itself is going to be in between the partial sum plus the integral from n to infinity of f of x and the partial sum plus the integral of n plus 1 to f of x dx. And we can use that inequality as well to get bounds, not just on the error, but to get bounds on the actual sum of the series. Okay, so let's look at this in practice. So if we want to find, given the following convergent series, let's find the upper and lower bounds for the remainder in terms of n. Given this specific remainder, let's figure out how many terms are needed to ensure that the remainder is less than 10 to the negative third. So let's go ahead and take a look at what we're talking about here. So if we have a series, it does say that this is a convergent series. In my instructions, I specifically typed that. But how do we know it's a convergent series? Well, this is a good practice. This is a P series, and P is equal to 3, which is greater than 1. So we know that this guy converges by the P series. So we already know it converges. So that means that this guy from k equals 1 to infinity of 1 over k to the third is equal to some sum. Now, what that sum is, that's the part that we don't know. But we do know that it equals some sum. So what we want to find, what we're being asked to do here, is we want to find R sub n so that R sub n is less than 10 to the negative third. We want to find the remainder, or the error. We want to find n. I wrote find R sub n, but we want to find n, not R sub n, so that R sub n is less than 10 to the negative third, so that the error in an estimation is less than 1 over 1,000. So we will be within 1/1000th, let's write that out, 1/1000th of the actual sum when we make our estimation. If we stopped at whatever n value is, if we added up the first n terms, I don't know, maybe it's 100, if I added up the first 100 terms, then I would be within 1,000. We want to figure out what is that n that would get me within 1/1000th of the actual sum, this sum. So how far do I have to go out, right? Obviously, if I go all the way to infinity, I'll find that exact value, but it's hard to add to infinity without having an infinite amount of time. Okay, so I pulled our remainder estimation for the integral test right here. And now we're going to plug in our function. So the first thing actually in my instructions, we wanted to find the upper and lower bounds for the remainder just in general in terms of n. So let's go ahead and plug into this inequality and we'll solve. And then we'll answer that question more specifically about how do we get this close to find the actual n we would need. So we want to find the remainder estimate for, oh, we should talk about what the function that would connect to this series. The function that we're looking at here is 1 over x to the third. And that is a, we already know it's a P series, so it meets the conditions, but that is a positive decreasing continuous function. So that did meet the conditions of the integral test. So we want to find the remainder estimates for n to infinity of 1 over x cubed dx and n plus 1 to infinity of 1 over x cubed dx. Now, each of these integrals is an improper integral. The work for each one of them is going to be very similar. So this is going to be the limit as t is approaching infinity of the integral from n to t. I'm going to write that as x to the negative third dx. On the other side, we're taking the limit as t is approaching infinity of the integral from n plus 1 to t of, same thing, x to the negative third dx. I made my x really big there. Let's make it a little smaller, x to the negative third. And now we're going to integrate. I'm going to zoom in a little bit. Now we're going to integrate on both sides, put my inequality back in there, and then evaluate across the bounds, and then take the limit. So the integral here, when we integrate, we get x to the -2 divided by -2. So I'm going to go ahead and just rewrite that. That is actually going to be -1/2x squared, and I'm going to be evaluating that from n to t. Now this integral on the other side, we're doing kind of repetitive work right here, because the only difference on these two sides is where that lower bound is in the integral. So we're doing repetitive work, so I'll just rewrite it -1/2x squared, and we're evaluating it from n plus 1 to t. And our remainder estimate, we're trying to get that upper and that lower bound there. This is going to be the limit as t is approaching infinity, and we're going to get -1/2t squared plus, because we're subtracting a negative, 1/2 n squared. And on this side, we get, in a very similar way, we get the limit as t is approaching infinity, -1/2t squared plus 1/2 times n plus 1 squared. And then we let t go to infinity on both of those limits, and that's going to give us a 0 here and a 0 here. And we find that our remainder, when we use n terms, when we use n terms to estimate the sum, that our remainder is going to be between 1/2n squared, less than 1/2n squared, and greater than 1/2 times n plus 1 squared. So that is the lower and the upper bounds on the error, or the remainder. So I didn't say anything specific, but if we had used 100 terms, if we had added up the first 100 terms, then the remainder would be between 1/2 times 100 squared and 1/2 times 101 squared. It would be in between those two values, the error, that we would have that amount of error in between. So that's the upper and the lower bounds. That answers the first question. Now let's talk about determine how many terms to get r sub n to be less than 10 to the -3rd. So now let's use our remainder estimate. We know what that's going to be an upper bound. We want our upper bound to be less than 10 to the -3rd, or 1/1000, 0.001. So we know from our generic work that r sub n has to be less than or equal to 1/2 times n squared. And we want that to be less than 1/1000. We want to figure out what n for the following. So we want to figure out what is the n we need in order to have that error be less than 1/1000. So we just take our upper bound here. We want our upper bound to be less than 1/1000, and we're going to solve. So let's see here. So we got, let's do a little cross multiplication. So 1000, those are both positive quantities, so we can multiply both sides by 1000 and multiply both sides by 2n squared. And then we get n squared is greater than 500. I'm going to rewrite it this way. N squared is greater than 500. I'm going to take the square root. That also will not affect the inequality. So n is greater than the square root of 500. So we need the n value to be greater than the square root of 500. Now, n needs to be an integer, because remember, we can't add up the square root of 500 numbers. We need an integer number. So let's actually calculate that. That ends up being 22, let's see on the calculator, 22.36 approximately. So n needs to be greater than or equal to 23. So what that is saying, in other words, what we're saying is find S sub 23. Remember what S sub 23 is. That would be from k equals 1 to 23 of 1 over, trying to look back at what series we were looking at, 1 over k cubed. Find that, which remember, that's going to be 1 plus 1 over 2 cubed plus 1 over 3 cubed. Add that all the way up, 1 over 23 cubed. And the difference between S and that 23rd, that sum of the first 23 terms will be less than 1 over 1,000. And so that's kind of an interesting thought right there. We know, right, we're talking about an infinite series here, like adding up an infinite number of numbers, but we just showed using that remainder theorem for the integral test, we just showed that if we added up for this particular series, if we added up just the first 23 terms, that we would be within 1/1000th of the actual sum, right? So we're talking about infinity versus 23, right? So if we needed to find an estimate, if we wanted to know what the sum was within some degree of error, then we could do that using this theorem. We could figure out what it is, what is the remainder estimate, like we did in the first step, and then we could actually calculate it to some degree of accuracy. Like, say we wanted it within 3 decimal places, that would be 1 over 1,000. Okay, so that's how we use the remainder estimate. It can be helpful if we need to know what the value of the series is to some degree of accuracy.